Okay, again, Assalamualaikum warahmatullahi wabarakatuh, and good morning, everybody. So let's revise our plan for this semester on DSP. Okay, so we have 14 weeks in total. So we have 14 weeks, and now we are actually in week 8. So week 8 means not including the semester break. So if we include semester break, it should be a week 9. Okay, so we have covered, if you look at those green color, so that green color is actually on time domain. So we have done on analysis on time domain. And then we did some analysis on the Z domain, so that red color things. And then week 6 last time, so that one is on system function. So this is where we convert between the impulse response and a difference equation, and vice versa. Okay, difference equation to impulse response to difference equation. And before the semester break, so we have some introduction on frequency domain. So that blue color. So we're going to have a 1, 2, 3, 4, 5 weeks for frequency domain. Okay, so we have a time domain, Z domain, which is a complex domain. Z domain is a complex domain. Last time in signal and system, so that Z is actually S. So S domain. Z domain is actually time domain to Z domain, you do a Z transform. But in a continuous time, so time domain to complex domain, so we do a Laplace transform. So last time we do Laplace transform. Now we're not going to do the Laplace transform, we do Z transform. Okay, so we finished that, and then so our journey on the frequency domain has started before the semester break. So you have been introduced to 5 different types of frequency. Okay, because maybe previously you know only maybe the most frequency that you know is a frequency in hertz. That one is a physical frequency, we call it. And then there's another one which is an angular frequency. But in discrete time, signal and system, so we have another 3 type of frequency. Okay, so today we're going to continue on DTFT. We're going to look at the formulation. We're going to look at on the plot. So how are you going to plot the frequency domain? Okay, so time domain is our original signal, and then we need to look on something. So we do a transform. Okay, so that's why this is part 2. Part 1 is actually from last week, and this is from last week. So what are those 5 frequency type? So actually we have a F, capital F. So this is in unit hertz. Okay, what we call it, this is what we call a physical frequency. And then we have an angular frequency. So this is an angular frequency, which is the unit is in radian per second. And then after we do sampling, because this one is actually in a continuous time. Then do sampling, time sampling, so you will have this small f and small omega. That small f and small omega is that small f doesn't have any units because this is a frequency ratio. Okay, or sometimes we call it a normalized frequency. And this is a small omega, which is the angular frequency of this frequency ratio. So because this is there's no unit for this one, so that's why the unit for this angular frequency is actually just a radian compared to this one. So this is the radian per second. Okay, because f units hertz is actually 1/second. Okay, and because if we look at this one, so this is actually continuous time, continuous frequency. So the frequency is continuous after we do sampling in time. So what we do convert continuous values is only the time, not the frequency, only time. So this is what we call as time sampling, right? So even though we have a discrete time, so the frequency is still continuous. So here, the frequency is continuous. So that's why we need another sampling. So this is where we call it a frequency sampling. So after we do a frequency sampling, so we will have what we call a discrete frequency. So we denote it as a K. So in this course, we denote it as a K. So those are the 5 frequency that we're going to look at in this course. Okay, so we have additional 3 frequency compared to the previous courses. Okay, previous courses is just capital F, capital omega. So now we have another 3 because of two sampling process. One is a time sampling, another one is a frequency sampling. Okay. So all right. So let's read this. So what is actually and let's go back to what is our title. So the title here is, if you realize, so this is what we call a discrete time Fourier transform, or in short, so this is what we call a DTFT. Okay, and those who did assignment on frequency plotting, so I can see that you guys already discussed on this one, DTFT and DFT. DTFT versus DFT, and that's quite clear. So those who post that idea, so saying that DTFT is just theoretical. So actually, we cannot implement that. The one that we can implement is actually DFT. Okay, so let's see why is that? So why is that? Okay, so for now, this is a discrete time Fourier transform, which is a DTFT. So not yet. This one later. Okay, DFT later. Okay, so and okay, again, when we look at this one, so the one which is discrete is actually why the name is very specific, discrete time Fourier transform, because the only variable which is discrete is the time. Okay, so that's the difference with DFT. DFT is this is a full discrete. The time is discrete. The frequency is discrete. Okay, but we need to start our discussion before we can go to this DFT. We need to start our discussion on DTFT, which is discrete. The time, the only discrete value is the time. Okay, we hold the frequency first. So we're going to discuss here in this topic, the frequency will be still continuous. Okay, still continuous. Okay, and actually DTFT, or Fourier transform, is actually a subset of a Z transform. So we have seen Z transform, we have seen the formula of a Z transform, and a Fourier transform is just a subset. So the formula will be almost the same. Okay, it will be almost the same. So what is a Z transform? As Z plane is a complex number, so this is a complex number. We can write it as a Rej omega, or we can write it as a plus JB, where A is actually real value and B is the imaginary value. Okay, so this is in polar form. We call it polar form. So this is in Cartesian form. Okay, coordinate form. So, and for Fourier transform, that R, what is the R? R is the radius. Okay, that R is actually equals to 1. So that's the only difference between a Z transform and Fourier transform. So what is Fourier transform? Fourier transform is actually Z transform when R equals to 1. So what is a Z? Z is a Rej omega because Z is complex value. Okay, then now we just change this one. R equals to 1. So what's left is Ej omega. So that's why this is where if we are looking at this Z transform formula, if you remember, so this is a summation of our input signal or our input vector. It can be a signal, it can be a system. Hn is a system. Okay. So what is a Hn? Hn is an impulse response. So what is the impulse response? An impulse response representing system. Okay, but of course, this is just a vector, a sequence of values. Okay, Hn is a sequence of values. And of course, we can do this on a signal. Okay, we can change that. We can do, no problem, because we can do it on Xn. Then you will get Xz. Okay, and this is not a system, this is a signal. So we can do on both, on system, on signal, right? And normally Xn is an input signal. Okay, normally Xn is an input signal, and output normally we denote it as a Yn. Okay, so because we just changing this Z, now this Z, we're going to change it into EJ omega instead of REJ omega, because originally the full of a complex value in polar form is a radius multiplied by the exponent of J omega. And now because the R is equals to 1. So what's left is a EJ omega. Then this is a formula of a DTFT, almost similar to a Z transform, and even actually simpler because now it doesn't have the R. Okay, because the R is actually equals to 1, we can just we doesn't have to write it. Okay, so it becomes a summation of a Hn E minus J omega n. Okay, and if you realize here, so we have this. So we have this omega. So what is omega? Omega is our frequency. All right. So if you still remember just now from last week, so we have this omega. Okay, and this frequency is in radian. And what is this? Specifically, this is angular frequency for discrete time, signal or system. Okay, so when we have a discrete time system, so we will have angular frequency, which is a small omega. If we have a continuous time system or signal, so we will use this a capital omega, right? So this is where it comes from. So where is that omega? So this is actually the Z domain. So we have this angle, this angle value. Actually, that angle value is a frequency. So that is actually the frequency, right? And it is in radian. So we can have a frequency from 0, and then it goes to pi over 2 here, pi over 2, 90 degree, and then this is a pi. Okay, and this is not just pi, this is also negative pi. We can also say it as a negative pi, because if you start it from here, 0, so this is negative pi over 2, this is also negative pi, right? Because that's how angular things work on the cosine and sine signal. So it seems like symmetry. Okay, so this part and this part, so we call it conjugate. So it seems symmetry. Okay, but that symmetricity is we call it a conjugate. So what is a conjugate? The conjugate is the real value will be the same sign, but the imaginary value will be on opposite sign. So that's what we call a conjugate. And yes, of course, this cos, now actually when we go to a frequency domain, so the things becomes a bit complicated, because maybe there will be a lot of maths. Okay, I will talk about exponent. I will talk about complex value, those kind of things. Trigonometry. Okay, so try to do some revision on those kind of maths, right? Because we doesn't want that we should learn concept of a DSP, but to learn that concept of a DSP, so we need to have a strong basic on maths first. Okay, and actually those kind of thing you have seen that many times. So just do some a little bit of some revision. I think you will get back. You will remember everything. Okay, then coming to this class will be much easier. Okay, so this is forward. Forward means we have from time domain, and then you transform it into frequency domain. So we will have a new plot. Okay, this is a plot on frequency domain. So we have a plot on a time domain. So that's why the assignment is very important, so that you can imagine if you have a time domain signal, so how do you plot it? So how will it looks like? So you have the x-axis, which is t or n. Okay, so in time domain, but in frequency domain, the x-axis will be will be frequency. So you should be able to imagine that. So that's why the assignment is very, very, very important. Okay, so if not, so it's very difficult to imagine this. And what is the inverse? So the inverse, the formula is you need to do some integration. And because this class, so we're not going to do integration. Okay, integration is actually too complicated. Okay, so we will do something else. So now we will focus on this one first. How to do the inverse? Later we're going to look at some methods, which is not involve this integration. Okay. So note that the inverse Fourier transform evaluated from omega from minus pi to pi or with the range of 2 pi. This is because omega value will be repeated after each 2 pi. Okay, just ignore that one first. And this is actually more general. Why we do DTFT actually is just why we need to transform our time domain signal into a frequency domain, right? So actually why we do that. So basically, so what's written here, basically signal has 3 information: amplitude, frequency, and phase. So actually this is discovered by Fourier. Fourier is actually a person. Okay, I think everybody already know this because we have seen a Fourier transform since at least year 2. Okay, so Fourier is a person. So what Fourier discovered is, that it says that theoretically all signals can be decomposed into sine and cosine signal, right? Any signal. So whatever signal that you have, so you can decompose. Decompose means you can separate. Okay, we can separate this signal into a cos and sine signal. So plus, maybe this is higher frequency, plus more. Maybe this is a small amplitude. Okay, but of course you need to plus. So how many sinusoidal signal that you will have? So normally it will be infinity number of signal. Okay, so and what is this? What is from our previous class? We already know that sinusoidal signal is actually either cos or sine. So it has a single frequency. So that's what we want. So that's actually what Fourier discovered and says that if we can decompose this into a single frequency signal, so then we can rearrange this one into a new plot. Okay, rather than plotting it in time domain, which is the x-axis is time. So we can rearrange that into frequency. So we change the x-axis from time into frequency, and we can see something else. So we can see something else. Okay, a more meaningful information. So that's why we do that. And because what is actually frequency? Frequency is something like something which is repeated. So that's why we call it frequency. Frequent. So how frequent it is actually repeating. Okay, so signal is actually that's actually some the properties of a signal. So most signal is actually repeating. Okay. So, but plotting it on time domain, we cannot see the repetition. So where is the repetition here? So it's very difficult to identify. Okay. But if we do this one, we decompose it into this sinusoidal signal. So then we can say that, okay, this one repeat somewhere here. Where does this repeat? So it is somewhere here. So this is where we can do some analysis on frequency. So, and for our case, so what we will do is actually filtering. So in signal filtering system, so filtering is actually based on frequency. So that's because a signal has a frequency. And what will be the idea? The idea is actually when we want to do some filtering, so we are filtering frequency. Okay, so that's why you have heard about low pass filter, high pass filter, band pass filter. band stop filter. Okay, so what are those things? What is a low pass filter? What is actually being passed through when you say low pass? Okay, what have been passed through? So low pass means you're going to pass through low frequency, and you're going to attenuate or remove the higher frequency. Okay, so that was what it means by low pass, high pass, band stop, and other types of filter. Yeah, actually, those are the basic filter type. Yeah, of course, we can have other types of filter. A combination of those four, right? So actually, all filter, the most basic is actually low pass filter. Other types of filter can be derived from low pass filter. Okay, so what is the point here? Frequency. So we will work on frequency. So this is after when Fourier says that we can actually decompose our signal into frequencies. So we are working on the frequencies now, okay, because of Fourier. Of the signal where the desired frequency component will be preserved while the unwanted frequency component will be removed from the signal. So that's actually filtering. A filter is actually, concept of filter is quite easy. So maybe it is the same like if you have a water filter, you're going to filter some maybe something from it, so that you will have a very a nice water, a clear water. Okay, so that's filter. In this case, a Fourier transform is used to sort the signal based on its frequency, because we want to filter some frequency, so we need to sort our signal, because originally we have a signal in time domain, so you need to sort it back into frequency. So after we do that, then we can easily design a filter to remove any of the frequency that we doesn't want. Okay, those are unwanted frequency. We can just remove it, because we can see where's the frequency, where's the low frequency, where's the high frequency. So where is the noise? So where is the desired frequency? So we can see those things in the frequency plot. Okay, so that's why we need to do a Fourier transform. And in this class, which type of Fourier transform that we will cover is a discrete time Fourier transform. Okay, because we are dealing with discrete time signal and system. All right, so last time when you do a signal and system causes, cause and other causes, there is several other causes that do a Fourier transform. So you just do Fourier transform, because you are dealing with continuous time. For continuous time, we don't put it as CTFT. Okay, commonly it doesn't do that. So it's just that if you have a discrete time, so we put it as a DTFT. So if it is just FT for the transform, that one is for continuous time. Okay, and of course, last time you have seen also what we call a Fourier series. Okay, we're not going to discuss that because we're going to focus on discrete time Fourier transform. So, but what is the purpose? The purpose is the same. If you do Fourier transform for continuous time, discrete time, the purpose is the same. So we want to see the frequency component of our signal or system. Okay, so that we can do some analysis. We can do some design. So because that will be easier to do it, rather than just looking at the time domain signal, which is there's not much to analyze. So in continuous signal, frequency is labeled as F and the units is Hertz. So we have discussed this in our previous class. So this is actually also from our previous class. So we have capital F, which is in Hertz, and then we have this small f, okay, which is the ratio of F and Fs, no units. And sometimes we call it as a normalized frequency, because the range is from 0 to 1. When something has a range from 0 to 1, okay, anything in maths, if you have a range of 0 to 1, so that one we call it normalized value, right? Normalized value. So the same with this. So we'll see that the value is actually from 0 to 1. So, okay, so we have covered this. We have this capital omega, one type of the frequency, which is the angular frequency, which is equal to 2 pi f. So this is our physical frequency. And for discrete time signal, So we have a small omega, which is the unit is a radian, and this is actually angular frequency for our normalized frequency. This is why we have this, because we have a sampling. From this to this, why this is happening? Because we have sampling. Okay, because of sampling. So then we can also write, because previously, if you, okay, let's go back a bit on the formula. So where is the formula again? So either you write this formula in terms of Ej omega. This is angular frequency. So you have an angular frequency here. So you can convert this into, you can change this into a small f. So what is a small f? What is actually omega? Omega is a 2 pi f. So then you can just write that equation again. This is the same equation. It's just how the way we write it. You can just do this hf. Then that omega is changed into 2 pi f. So previously we have seen that this is actually j omega. Okay. If you write it as a h omega, so that one will be n minus infinity up to infinity of a hn e minus j omega. So that's just some notation. Okay, so you can write it as a hf, you can write it as a h omega, doesn't matter, because this is exactly the same equation. And this is a full notation, just to make sure that everybody realize that if you have a continuous time in time domain, so we put it as a xt. Okay, so when we have a x, so this is actually a signal, and normally this is an input signal. Okay, t, and we are using a normal bracket here, and in the frequency domain for this continuous time, so we're going to have time domain. We use a small x. Then we use a capital X for frequency domain. Same here, discrete time. The x is a small x. Then we use a capital X for frequency domain. And this is a continuous frequency in continuous time. So we have angular frequency, and this is a physical frequency. But in discrete time, so we have omega and f. And if you look at this notation, x, because n is discrete, so we use a square bracket. We use a square bracket. And if you look at this notation, the frequency domain, so you're not using a square bracket, because that omega, that small omega, and that small f is not discrete. This is continuous. Okay, even we are trying to, in this course, we try to make a consistent notation. By looking at the notation, you will know that, okay, that omega is not discrete, because we are using just a normal bracket. This bracket is a square bracket, and we know that n is discrete. Okay, so continuous, discrete. So far, so we've seen only one discrete. So one frequency, another frequency, the third frequency, the fourth frequency. We have another frequency, which is a discrete frequency. That one we will cover that later. Okay, so just a few more things. In this first session, we're going to look in a few more things, and then second session later. So we're going to look at some example on how we will work on this formula. All right, so another thing that we need to know in our DTFT, the discrete time Fourier transform, is about this thing, which is a magnitude and phase spectrum. So because similar to Z transform, so the results of a Fourier transform, after we do that formula, the summation of Hn multiplied by e to the power of minus j omega, right? J omega n. So that one is actually we will get complex value because Fourier transform is just a subset of a Z transform. Z transform is actually a complex plane. So because of that, thus to obtain the behavior of the signal, magnitude and phase spectrum are used for analysis. So we're not going to analyze the real and imaginary plot, okay? But a more meaningful plot will be the magnitude and phase. Okay, so why do we have this magnitude and phase? Because the result is actually a complex value. So complex value means, so we have actually this one, okay. H omega, actually this H omega is, one part of it is a real value, the real value of the transform. And then we have an imaginary of the transform. So that's complex value. How do we get this? Because if you look at this formula, so we have a e to the power of minus j, right? So this will give us the complex value. And this is actually from a trigonometry. So what is the e minus a j omega? So that one is actually cos omega plus minus j sine omega, okay? The real part is the cos omega. The imaginary part will be the minus sine omega. So that's from trigonometry. So we're going to look at that one later. We call it an Euler formula. So originally, after we do that, after we do the calculation using that formula, so which formula? The formula of a summation of Hn multiplied by E minus J omega n. So we will get this one. But this is actually not really meaningful. So we need to convert it into magnitude and phase. So these are the one that we're going to analyze. So how to get magnitude? Very easy. So this is very a basic math. So real squared plus imaginary squared square root. So that's magnitude. Okay, and what is phase? Phase, again, this is quite a basic math. So how do you get phase? So it's just a tangent inverse of the imaginary divided by real. Okay, so you have the imaginary part, what will be the value, and then look at the real value, and then just do this. Just do this formula. So we'll get the phase. We get the magnitude, we get the phase. Okay, so then we will analyze this later. And other spectrum representation other than magnitude and phase. So sometimes, so we're going to plot energy. So what is energy? Energy is magnitude square. Okay, so actually energy is just a magnitude square. And the magnitude square is actually just H omega, the original H omega, the one which is in the form of real plus imaginary. So that one. Multiply with, so what does this mean? Conjugate. Okay, that star, if you have H omega, and then you need to multiply with the conjugate of the value. So conjugate is not that, it's actually it's quite simple. So let's say we have, let's say we have a H equals to a 2 plus 3J. So what is the conjugate? The conjugate is simply 2 minus 3G. Okay, different sign of the imaginary part. So that's all. That's what it means by conjugate. So the same value, different sign on imaginary. So then, if you do this, so what is the energy? Energy is actually just equals to that H, and then you multiply with H conjugate. Okay, then just multiply these two. So multiply that one. 2 plus 3J, and then just multiply by 2 minus 3J. Okay, simple multiplication. 2 multiplied by 2 is 2, 2 multiplied by minus 3J, and then plus 3J multiplied by 2, and then this 3J multiplied by minus 3J. So that J and J multiply, so you get minus 1. Okay, so then what you will have is, why do we do that? Because we want to cancel out cancel out the imaginary parts. Because this is actually just a 4 minus a 6j plus 6j minus 3 minus 1. Sorry, 9. Okay, remove. So this is just a 4 plus 9, which is equals to 13. So this is where we can see that if we do energy, so you will always get positive value. Okay? You will always get a positive value. The same with magnitude. Magnitude, you should always get a positive value. The other one is magnitude dB. Okay, so why is this? Why we do this? Why sometimes we plot magnitude dB? Even actually from your previous courses, including that signal and system. So and maybe from I think a control system. So you have seen a lot on dB plot. Okay, you have seen a lot on that one, on the dB plot. So you have seen what it is that minus 3 dB, minus 6 dB. So you have analyzed those kind of things, and everything is in dB. So why we do that? So actually is to obtain clearer plots, as most of H omega values are small. Okay. So actually dB is just we are rearrange, not rearrange. So what is the term? We will set the value into a new range so that we can see all values. So that's what dB means. Even if you realize when we measure sound pressure, okay, if you measure sound pressure, the unit is in dB. So why is it in dB? Because at certain, let's say for a very quiet place, so maybe the value is very small. And then if it goes like people are talking, so the value becomes a bit high. And then if it is on maybe a side of a road, so the value becomes many times higher than people talking. So those value is actually from a quiet place until maybe a concert. So the range is very wide. Okay, so when you do let's say look into a concert sound pressure, you won't see a value of the when people just are talking in a room. That's why we rearrange the value so that we can see all values. Someone raise a hand?
Yes, sir, I have a question.
Yes, please.
The converting to dB, right? Is it the same as normalization?
It's not normalization. Normalization is when you say normalization, so you change a value into a range of 0 to 1.
Yeah.
Okay. So this is normalization is you rearrange a value. Okay, you set a new range. dB is also doing the same thing, but the range is not 0 to 1.
Oh,
It is on a different range. It is a different range. What is the purpose? The purpose is actually both are rearranging values into a new range.
Thank you for the clarification, Doctor.
And actually, that's very important. When we do normalization, we want to have everything actually to reside on the same range, 0 to 1. Okay, so because sometimes we have values on a different range. One value range is 0 to 100. And then another value, the range is maybe from 0 up to 50 only. So both are not the same range. Then we normalize everything so that everything becomes from 0 to 1. But dB, we rearrange value not for that purpose. So we do that because we want to see so that we can observe a smaller value. So that's why we can see that if you have a very small value, then the value will become bigger. Okay. So then we can have everything. So this is just for analysis. We're not going to convert everything into dB for calculation. When we do filtering and everything, which involve some calculation, so we're not going to convert it into dB. So dB is just for us to do some analysis on it, and for us to do some observation, visualization, so that we can see everything. Okay, so that's dB. Okay, and then okay, so those are the things that we have here. So we have magnitude, so we have a phase, so we have energy, and we have dB. So this is the last one before we take a break and to this first session. So this is the DTFT plot. So what we need to understand is whenever we have a signal, so we need to know how to plot it. Okay, in time domain. So what we have is actually time domain. Why is it called time domain? Because the x-axis is time. So that domain, when you call it time, so actually it is referring to the x-axis. Okay, so this is t. T is or in discrete, so it is actually n. Okay, t is a continuous. T is a continuous, and this is in n. And I see some of the discussion in I think plotting in time domain. So I think one of the posts is actually discussing on how to convert between these t and n, which is very good. So which is very good. Okay, so now those group have seen so how to plot if you have an n. So if you have t, how do you use the frequency sampling to convert from this n into t? Okay, so I see that the code. So very, very good. So that was a very good post. Okay, and normally y-axis is of course what we call amplitude. Amplitude can be if you are actually measuring voltage, so it will be voltage. If you are measuring current, so it will be current. So if you are measuring pressure, so it will be pressure. So it depends on your sensor. Okay, it depends on your sensor, or it depends on your device. So what is actually the measure that you are measuring? But the x-axis is time. So this is actually our original signal. So our original signal, which is maybe it doesn't give us a lot. So this is where we need to do the Fourier transform. And when we do for Fourier transform, of course, then it will be called a frequency domain. And again, because this is a time domain, the x-axis is time. And frequency domain, the x-axis supposed to be frequency. The y-axis, those are the things. It can be magnitude, it can be phase, it can be energy, it can be magnitude, dB. So that's the y-axis. So if we are plotting magnitude, so we get a magnitude plot. If you are plotting phase, we get a phase plot. Okay, so we can plot either 4 of these and then do analysis. Okay, so we need this to do the analysis. And the frequency, we already know that. So we have 5 types of frequency. So the frequency can be the f, it can be capital omega, it can be small f, it can be small omega, and it can be k. So we have 1, 2, 3, 4, 5. Right? So these are actually the frequency plots. So either you're going to plot either of these 4 and versus one of these frequency. Okay, we're not going to plot every time on all the frequency. So we need to pick one of the frequency. We need to pick one of the measure. And later we're going to do some analysis on it. Magnitude has its own purpose. Phase has its own information. Energy has its own information. Magnitude dB has its own purpose. So why we do that? Okay. So okay, so we will stop here. We will start again on our second session. I will post the link for second session just a while, right? So and then we're going to look at range of this frequency, because we need to understand that first. So what is the range of this thing? If not, you're going to have a wrong plot. So we need to understand the plot first. Okay, so okay, we stop here. So we will start again at 10 minutes. Okay, 10 minutes. So have a break first for 10 minutes. Okay, bye everybody. See you guys in 10 minutes.
See you, Doctor.